Welcome to today's class. Today we are going to look at some concepts of probability that are useful in econometrics. In business, we are constantly faced with uncertainty, and management have to make decisions in the face of such uncertainty without having much clue how the future will look like. Probabilities help us to deal with uncertainty and to evaluate the possibility of occurrence of certain events of interest. So what is probability? Probability is a measure of likelihood of occurrence of a random event. A random event is one where the outcomes cannot be predicted with certainty. For example, suppose we toss a coin once. The outcome of the toss is unknown and unpredictable. It can either be a head or a tail. Now, the probability of occurrence of an event lies between 0 and 1. The closer the probability of an event is to 1, the more likely it is for that event to occur. And the closer the probability of the event to 0, the less likely the occurrence of that event. An event whose probability is 1 is said to be a sure event. That is, it is an event that will certainly occur. And an event whose probability is 0 is said to be an impossible event. It is an event that cannot occur. The probability of an event E occurring is denoted by the symbol probability E, that is PE. The set of all possible outcomes of a random event is known as sample space of the event. For example, suppose we toss a 6-sided die once. We have 6 possible outcomes. So the sample space is 1, 2, 3, 4, 5, and 6. A subset of outcomes in a sample space is known as an event. Let A be the event that in a single toss of a die, a number less than or equal to 3 turns up. Event A has outcomes 1, 2, 3. A set of outcomes in a sample space not in the event is known as the complement of that event. It is the event that a said event won't occur. For example, the complement of event A, which we denote as A bar, is the set of all outcomes that were not in the event A, that is 4, 5, and 6. Let's now look at the types of probability. There are 3 types of probabilities: theoretical, empirical, and subjective. In theoretical probability, computation of probabilities is based on the assumption that all outcomes are equally likely to occur. For example, if you toss a coin once, the likely outcomes are head or tail. We have 2 possible outcomes that are assumed to be equally likely. So the probability of a head will be equal to the probability of a tail, and that will be 1/2. Suppose the coin is tossed twice. What is the set of all possible outcomes? I leave that one as an exercise for you. In general, for theoretical probability, the probability of an event occurring is given by dividing the number of outcomes favoring the occurrence of the event with the total number of possible outcomes. The other type of probability is empirical, also known as experimental probability, which refers to probability based on historical data. For example, suppose we toss a coin 50 times and 29 heads turn up. Then the probability of a head is 29 out of 50. In general, with empirical probability, the probability of an event E is the number of times the event has occurred divided by the total number of occurrences. Finally, we have subjective probability, which is probability based on personal intuition or intelligent guesses. For example, a production manager may assign a probability of 0.7 to the probability of success of a new product. But a marketing manager may feel the market is not that ready for the product and assign a probability of 0.4. This is subjective probability based on experiences and how optimistic or pessimistic one is. Let's illustrate a little bit using an example. A six-sided die is tossed twice. Each toss has 6 possible outcomes. Can we list them? Let event E be the sum of the numbers that turn up. What is the sample space of event E? What is the probability that the sum is less than 7? 2, the sum is 6. The set of all possible values for the sum can be listed in a table as follows. From the table, we see the sum ranges from 2 to 12, and thus the sample space is 2, 3, all the way up to 12. To compute the probability that the sum is less than 7, we count the number of outcomes for which the sum is less than 7. And there are 15 out of 36 outcomes for which the sum is less than 7. Hence, the probability that the sum is less than 7 is 15 out of 36. Similarly, there are 5 outcomes for which the sum is equal to 6. Hence, the probability the sum is 6 is 5 out of 6. Consider a production line where items are randomly sampled and checked for manufacture defects. The experiment of testing a randomly sampled item for defect is a random event with an outcome of a defective or good item. The quality control manager may be interested in the frequency of defects or the mean number of defects per production batch. This analysis requires the use of numbers, but the outcomes of the testing is a non-numerical value, defective or good. How do we link non-numerical outcomes to numerical values? We use random variables. A random variable is a variable whose value is determined by the outcomes of a random event. Random variables are denoted by letter symbols, e.g. x, y, z, etc. For example, we can define x to be the number of defective items in a randomly selected batch. Note, x associates outcomes of testing defectives to numbers by counting the number of defects. So if we get one defective item in a batch, x is equal to 1. A random variable that assigns countable number of values to random outcomes is known as a discrete random variable. For example, the random variable x defined as the number of defectives, is discrete since number of defects are countable. They can be 1, 2, 3, and so on. A random variable that associates random outcomes with uncountable numbers is a continuous random variable. For example, suppose customers arrive at an ATM service counter. Let X be the time each customer spends at the ATM. Time is continuous and can be expressed in fractions of seconds. It is thus not possible to pinpoint the exact time a customer arrives unless we approximate to the hour, minute, or second, and so on. Hence, X is a continuous random variable. Consider this example on your own and answer the questions. Let's now consider an example of tossing a six-sided die twice, with X being the sum of the two sides that turn up. The values of X and their respective probabilities can be presented in a table as shown. These probabilities depend on the frequency of the respective outcomes, just as we had discussed earlier. Such a table is known as a probability distribution table. We can also present this information graphically using a histogram. The histogram here shows the probability distribution of the values of X. Take note of the distribution curve. A probability distribution shows how the probabilities of a random variable are distributed. It helps us to summarize probabilities and also to compute them more efficiently and faster, instead of first of all listing all the possible outcomes and then doing the physical counts. We can use mathematics to define a function that describes the probability curve of a random variable. Such a function, if it exists, is known as a probability distribution function, denoted as Px. Knowledge of the probability distribution function helps us to compute the probabilities more efficiently. For discrete random variables, the probability distribution function gives us the probability that X is equal to some value small x. The probability distribution function has the following properties. 1. The sum of values lie between 0 and 1. Number 2. The sum of probabilities over all values of X is 1, which is written as summation Px over all X is equal to 1. This property is very useful in manipulating probabilities. For an illustration, let's consider the following example. Jeff tossed a coin and recorded the number of heads that turned up in each set of 10 tosses. Let X be the number of heads that turn up in 10 tosses. The table below shows Jeff's outcomes. Determine the probability distribution of X. The probability distribution is obtained by dividing the frequencies by the sum of frequencies. The sum of frequencies is 100. So we obtain probabilities of X by dividing each frequency by 100. For example, the frequency when X is equal to 6 is 23. So the probability that x is equal to 6 is 23 over 100, which is equal to 0.23, which is shown here. The probability distribution of x can be presented in a graph. The probability distribution curve is obtained by plotting the probabilities against the number of heads. Notice the curve is slightly skewed to the left, that is stretched to the left. This is the stretch here, to the left. Which indicates that this is not a fair coin. A fair coin is one where the probability of a head or a tail are equal. Of great interest when working with probability distributions is the central location of the values of a random variable, as well as the variance. The most popular measure of central location is the mean, which is known as the expected value of a random variable. It is denoted as mu or EX. Mu is spelled as MU. To compute the mean of a discrete random variable, we multiply each value by its respective probability, then sum that product. We write in short, mu is equal to the summation of the product xi times its respective probability. First of all, we multiply this and then we sum. Let's consider the previous example where we had 10 tosses of a coin. To compute the expected value, first multiply the probabilities with their respective values of x, then sum the products. When we sum the products, we get 5.9. This means that if we keep on tossing the coin, the expected number of heads to turn up would be 5.9 per every 10 tosses. Well, the expected value tells us about the central tendency of a random variable. It says little about the spread of the random variable. The variance is used to indicate the expected spread or deviation of the random variable from its expected value. The variance is denoted by sigma squared. For a discrete random variable, the variance is computed by first getting the deviations of each value from the mean mu, then square the deviations, multiply the deviations with the probabilities to get this product, and then sum all those products. That sum gives you the variance of the random variable. The average deviation from the expected value is given by the standard deviation, which is the square root of the variance. Let's use an example to illustrate this. We consider the same example where Jeff tossed a coin 10 times. Remember, we found the mean to be 5.9, which is our expected value. To compute the variance, we first compute the deviations from the expected value, mu, equal to 5.9. These are the deviations that we get here. Then we multiply the squared deviations with their respective probabilities. And this is the result which you get when you multiply. After that, we sum the squared deviations, and that sum gives us the variance. So in this case, the variance is 3.25. To get the standard deviation, we take the square root of the variance. And now we have our standard deviation here is 1.80. Let us turn our attention to some probability distribution functions that are commonly used in econometric modeling. Each probability distribution function has unique properties that describe it. We look at three common probability distribution functions, namely binomial, Poisson, and the normal, also known as Gaussian distribution. Our discussion will be restricted to their properties only. The binomial distribution is a discrete distribution and has the following properties. 1. There are a fixed number of trials n to be made. For example, in the previous example, Jeff tossed the coin 10 times. Hence, the number of trials n is 10. Number 2. Each outcome of the random event has only two mutually exclusive and exhaustive outcomes that can be classified as either success or fail. For example, tossing a coin, you get a head or tail, or testing a product for manufacture defect will yield a defect or no defect. Number 3, there is a fixed probability of success, which we denote as P. That is, the probability of success remains the same from one trial to the next. For example, if we toss a fair coin, the probability of a head is 0.5. This probability remains the same when we make the first toss, the second, or even the 20th. The probability of getting a head in any of the tosses remains 0.5, irrespective of the number of tosses. That is, in each of the tosses, the probability of a head remains the same throughout. The fourth property is that the outcome in each trial is independent of outcomes in the previous trials. So if we toss a coin 5 times, the outcome in the first toss is independent of the outcomes we had in the second and the other previous tosses. Now, the probability distribution function of a binomial random variable is given by the formula px equal to nx p to power x 1 minus p raised to power x. This one is the probability that the event does not occur. This is the probability that you get a success, probability that you don't get a success. And this one, remember, means n combination x. The expected value of a binomial random variable is the product of the number of trials n and the probability p of success, while the variance is given by the product of n, p, and 1 minus p. Next, we look at the Poisson distribution. The Poisson distribution is used in situations where the events occur in intervals of time or space. That is, the number of, the number of sales calls per hour, or the number of customers served at a counter per hour, and so on. A Poisson random variable has the following properties. 1. Events occur, as I have said, in intervals of time. Number 2, the probability that an event occurs within a given interval is the same for all such intervals. For example, the probability that a customer arrives at an ATM within an hour is the same irrespective of the hour in reference. That is, the probability a customer arrives between 9 and 10 a.m. is the same as the probability that a customer arrives between 11 and 12 p.m. Number 3, the number of events that occur within a given interval is independent of occurrence in previous intervals. For example, this means that the number of customers who arrive at an ATM is independent of the number of customers that had arrived in the previous hours. And number 4, for each interval, we can define a small interval such that the probability of 2 or more events occurring within such an interval is very, very small. So we can consider it to be 0. For example, we could expect that in a second, only one customer may arrive or no customer at all. It will be almost impossible to have 2 or more customers arrive at exactly the same second. Now, the Poisson distribution is defined by the average rate of occurrences per interval or space, and this is denoted by lambda. This one is known as lambda. The probability distribution of a Poisson random variable is given by the formula px equal to lambda raised to power x e raised to minus lambda over x factorial. And you can see the values of x are 1, 2, 3, 4 up to n. Therefore, the Poisson distribution is a discrete random variable. The mean of a Poisson random variable is equal to lambda, and so is its variance. The normal distribution, also known as the Gaussian distribution, is most popular among probability distributions. It is known for its bell-shaped curve that is centered around the mean mu. This one here. It is a continuous distribution and has the following properties. Number 1, it is defined by stating the mean mu and the variance sigma squared. 2, it is symmetric about the mean, which means that you have 50% of the values below the mean and 50% above the mean. Number 3 is that it has a single mode, that is, it is unimodal. And number 4, the mean, the median, and the mode are all equal. And lastly, the area under the curve is equal to 1. The symmetric property of the normal distribution implies that the normal curve is such that approximately 68% of the values lie 1 standard deviation from the mean, with 34% of the values above here and 34% below within here. 95% of the values lie 2 standard deviations from the mean. which means that you have got 47.5% of the values below the mean, and another 47.5% of the values above the mean, uniformly distributed on both sides of the mean. And lastly, you have 99.7% of the values lying 3 standard deviations from the mean. This is a very important property of the normal distribution, and it becomes very useful when you are computing probabilities of the normal random variables. Let's look at a special normal random variable, which we refer to as the standard normal random variable. A normal random variable with mean mu and variance sigma squared is symbolized as x, as shown here. This is the way we write in short form. So when you see this, then we are saying that x is a normal random variable with mean mu and variance sigma squared. Now, a standard normal random variable is one where the mean is 0 and the variance is 1. Its distribution is known as the standard normal curve. And as you can see, it is centered around 0 because the mean is 0. And then these are the deviations. So the cool thing with the standard normal random variable is that the numbers here you see, these ones, tell you how many standard deviations your values are from the mean. So this is 1 standard deviation from the mean and 1 standard deviation below the mean, 2 standard deviations below the mean, 2 standard deviations above the mean, 3 standard deviations below the mean, and 3 standard deviations above the mean. Just like the normal random variable, you have got 68% of the values 1 standard deviations away from the mean, and 95% 2 standard deviations from the mean, and 99.7% of the values 3 standard deviations from the mean. Any normal random variable with mean, mu, and variance sigma squared can be transformed to a standard normal random variable by subtracting the mean and dividing the difference by the standard deviation sigma. This is known as the z-score. The standard normal curve is used to compute probabilities of normal random variables. We shall be encountering the normal random variable many times in econometrics. Thank you. This marks the end of our lesson today. Have a good one and take care of yourself.